Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good day. Sorry, I'm recording on my car. So, I have a question. One of you asking about the electrochemical impedance spectroscopy. So, in the question, he asked me how actually to understand about EIS. So, what can I tell you? The electrochemical impedance spectroscopy, or commonly known as EIS, is a common analysis if you are study either energy storage or energy conversion. So in terms of EIS, what we are looking for in the graph, actually we are looking on the Nyquist plot. If your characterization involve energy harvesting, for example solar cell, you can also calculate the electron lifetime by using the Bode plot to see the frequency. From that you can do the calculation and formulation. You can get electron lifetime and also charge collection efficiency. But in terms of energy storage, so when we talk about energy storage, the same thing from the Nyquist plot. You can get first RS, some call series resistant, some call equivalent series resistant, ESR. Okay, a lot of name also they call series resistant and everything. Normally these RS, where the position is located at the left hand side of your Nyquist plot, we call that at high frequency region. So the RS at high frequency region normally belong to the total resistance of your system, including your solution resistance, electrolyte resistance, your electrode resistance. So it's a combination resistance on your material. That's why when you got your RS, the lower the RS is better, because it indicates the high conductivity of your material and your system. That's why we want to have a small RS as possible. Okay, in terms of what we talk about by saying in terms of application, a small RS, a small series resistance also depend on your what you call that substrate or current collector. So it's depend on your current collector. When you study, for example, lithium-ion battery, you are using copper foil, your RS might be very low, less than 10, maybe less than 1, maybe 1 to 5 ohm. So it's quite low. If you are using different current collector that have high, what we call that high resistance, low conductivity, for example ITO, indium tin oxide, FTO, the RS might slightly higher, around 20 something or 17 and all. Okay, it's depend on your substrate and depend on your material. The more the layer of your material, the higher the resistance, the RS might be higher. So you need to tailor your what we call the heterostructure, your layer to get a high RS. Normally we embed our material with a material that have high conductivity. For example, carbon-based material, graphene, MXene, and so on. So depend on your ability to produce new composite material, your RS will be dependent on that. Okay, that's the first thing first about the RS. Then we talk about the second important things is the semicircle. You can see half circle. That's why we call that semicircle. So that semicircle, the diameter represent the charge transfer resistance. We call that RCT. Okay. In solar cell, we got typically there are 3 semicircle presence at higher frequency, at middle frequency, and at lower frequency region. Normally at higher frequency due to the resistance of resistance of between counter electrode to TiO2 counter electrode interface. TiO2 counter electrode interface. In the middle is TiO2 photoanode interface, and at the end of the right hand side, a low frequency region, is depend on the resistance of your electrolyte. That's in the DSSC, typically in DSSC. You can refer to the journal for further clarification. But For supercapacitor normally we are talking about generally, they are looking for only one semicircle. Okay, from that semicircle, there exists the resistance of your material at certain interface. Then last but not least is your Warburg line. You can see a straight line like 45 to 90 degree. This Warburg line indicates the ion diffusion, how fast your ion can diffuse. I think that's a basic idea about electrical impedance spectroscopy. I hope by right, small or big, it can help you. If now my wife is also present, so I need to end the video. So later I will continue about the electrochemical impedance spectroscopy. Okay, bye. See you again.